gas laws allow us to interrelate a specific number of moles of a gas and analyze it with respect to changing specific parameters within a container or within a specific situation. So what do I mean by that? Well, the fact that we have a constant amount of the gas allows us to look at how a pressure or a volume or a temperature change will alter other variables within the specific gas law. And so the combined gas law interrelates pressure, volume, and temperature. So P1, V1, T1 represent the amount of gas at a specific pressure, volume, and temperature. P2, T2, and V2 represent a new set of conditions in which we can compare to the original set. So in this specific situation, if we have 5 of the 6 variables, we can manipulate the equation, isolate that variable, and subsequently see how that variable is going to change based on a new pressure or temperature or a new pressure and volume. And basically, we'll look at those details in a little bit. But the neat thing about the combined gas law is that you can get the other gas laws from this original combined gas law equation. Okay, so if you are at constant temperature, meaning that your temperature doesn't change, all you do is cross out your T1 and your T2, and you end up with P1V1 equals P2V2. If you're at constant pressure, you just cancel out your P1 and P2, and that gives you V1 over T1 equals V2 over T2. And then, of course, at constant volume, you can just cancel out the volumes, and you end up with the P1 over T1 equals P2 over T2. So all of these equations can be utilized in order to solve for basically the variable that's being observed. So, your volume or your temperature, your pressure. And depending on what you're given in the question, that's going to dictate the equation that you use. So we'll go ahead and look at that in a little bit more detail here soon. So before we start calculating with the gas laws, I want you guys to be aware that anytime you are doing your calculations and temperature is involved, you must make sure that your temperature are in units of Kelvin. So make sure you're making that conversion or else you're going to end up with the incorrect answer. Okay, so in order to solve this problem, the first step you always want to do with these is to first write out all your variables, so what you're given. Okay, so in the first situation, I'm given a volume. Okay, so we're going to denote that as volume 1 or V1 because it's our first set of data. Okay, the next value we're given is a pressure, so that's going to be P1. That's going to be written as follows. Okay, and then our T1 is going to be 22.5 degrees C. Now, as I said earlier, you want to make this conversion over to Kelvin, so you're going to add your 273.15, which is going to give you 295.7 Kelvin. Okay, so you make those adjustments, and then you go ahead and continue with the question. So they said, what will be its volume? Okay, so V2 is what we're solving for. What's going to be the new volume in the new conditions at STP? So remember, STP is 1 atm and 0 degrees C. You must memorize that. Okay, so in terms of my pressure, that's going to be 1 atm. Okay, and then, of course, we have our temperature 2, which is going to be 0 degrees C, plus 273.15. Okay, so that's going to be 273.15. Okay? So after you've figured out all of the variables, you can then look at what you've been given and figure out which equation you are going to use. So I've been given 2 temperatures, 2 pressures, a volume, and I'm wanting to solve for another volume. So in this case, you know already that you're going to be using your combined gas law. Okay, so you have these variables, so that's how you know what you're going to be solving for. Now, before you start plugging all your numbers in and going crazy in that regard, I first want you to be solving for the variable you're looking for. So in this case, V2. Okay, so how do I get V2 all by itself? Well, first I'm going to cross multiply, okay, my variables that are on the bottom. So you end up with P1 V1 T2 is equal to P2 V2 T1. Okay, so after you've done that, then you're going to isolate V2. Okay, so V2 is going to be equal to P1 V1 T2 divided by P2 and T1. Okay, so now that we've manipulated this equation, we can then start looking and making sure that we can plug in our variables. Now, the next thing that you need to check, okay, you know that you've already converted into Kelvin, so you're good to go in terms of those units. But the next thing you need to check is to see if your other units match. So notice, the units for pressure here are ATM, the units for pressure there are ATM. So because they are both the same units, you can go ahead and plug the numbers in accordingly. If you had ATM and torr or something like that, you would need to convert one or the other. So basically the units have to match. Okay, so we're going to go ahead and plug those in. So V2 is going to equal 0.90 ATM. Notice I'm plugging in my units as well. Okay, V1 is 2.0 liters. Our T2 is 273.15 Kelvin. Okay, that's all going to be divided by 1 ATM times, let's see, T1, which in this case is 295.7 Kelvin. Okay, now obviously we're going to just do the math, multiply all the numbers on the top, divide by the bottom, and that's going to give you 1.7 liters. Okay, and so how do I know I have liters? Let's go ahead and let's check. Okay, ATM and ATM cancel. Okay, so those cancel out, right? Kelvin and Kelvin cancels. What's left over? Liters. Okay, and does that make sense with what we've actually been told to solve for? Volume is what we were told to solve for. So what we've actually obtained in terms of our units makes sense. Okay, now listen. You must write out all your variables, manipulate the equation, solve for the variable that you're looking for, plug the numbers in, do a unit evaluation, and then give your answer. Okay, I will not be accepting answers that have, variables that are not labeled as V1, P1, T1, etc. Okay, I also am not going to be accepting just numbers plugged in without the manipulation first. And obviously, guys, you're going to get marked off if you don't plug your units in and do your unit evaluation. So please make sure you're being stepwise and, very, very fastidious about this. So now let's go on, now that we've looked at the combined gas law, let's go ahead and look at Boyle's law. Okay, so Boyle's law basically occurs when temperature is constant, right? Okay, and we've already established that we have a constant amount of gas. That's how we're basically interrelating the sets of variables. We're looking at that amount of gas at a certain set versus a new set of variables. Okay, so basically, Boyle's law allows us to relate pressure and volume. Okay, and as you can see from the graph here, you see that as pressure increases, okay, your volume is going to be decreasing. Or conversely, as volume increases, pressure decreases. So that relationship is something you want to be thinking about as you do your calculations, because you should, if you see a pressure change and the pressure, increases, then your volume of the variable that you're looking for should obviously be lower, okay, and vice versa. So if we go ahead and we take a look at this problem, okay, so once again, guys, you don't always know what you're going to be using, so the first thing you want to be doing is figuring out your variables. So a sample of chlorine gas occupies a volume of 946 milliliters. Okay, so V1 equals 946 milliliters. Okay, a pressure of 726 millimeters of mercury. Okay, so I've been given a volume and a pressure so far. Now it says, what is the pressure of the gas in millimeters of mercury if the volume is reduced at constant temperature to 154 mils? Okay, so they're telling you that you have a new volume of 154 milliliters. Okay, so that's your V2. Okay, and they want to know what the new pressure is going to be. So they've said that this occurs at constant temperature. Okay, so we know that we are using the P1V1 equals P2V2 equation, okay, or Boyle's law. And we're going to proceed just like we did in the previous example. So once you've written out all your variables and you've figured out which equation you're going to use, you're then going to solve for the variable you're looking for. So P2 is that variable. So we're going to have P1 over V1 divided by V2. That's going to equal the P2 that we are looking for. Okay, and then before we plug our numbers in into the equation, we want to make sure that our units match. Okay, so milliliters and milliliters, those are the same, so we can plug those in. Millimeters of mercury, okay, those are the units that we're wanting to solve for up here, so we can plug those in, and since pressure is what we're solving for over here, there's no need for those to match at this point. Okay, so we're going to plug the numbers in. So P2 is equal to P1, which is 726 millimeters of mercury. Okay, times V1, which is 946 milliliters. Okay, that's all going to get divided out by 154 milliliters, which is the V2. Okay, so you're going to go ahead and plug this into your calculator. And this is going to give you 4,460 millimeters of mercury. Okay, and so how am I getting that? Well, doing analysis. Milliliters and milliliters cancel. Millimeters of mercury are left over. Okay, so this is the answer. Okay, now if we take a look at this calculation, we should always ask ourselves, does this make sense? Okay, so the pressure at 946 milliliters is 726 millimeters of mercury. Now, I have decreased my volume by quite a bit, okay? If I decrease my volume, my pressure is going to increase, right? So that's what we would expect to happen, right? If we make the container smaller, basically those gas particles are going to bump up against the sides of the container more frequently, and subsequently your pressure value will be higher. Okay, so this is what we anticipate, and this is what we actually see. The 4,460 millimeters of mercury is quite a bit larger than 726 millimeters of mercury. So in terms of the magnitude change that we see, it makes sense. Okay, so on this slide we have Charles's and Gay-Lussac's laws. Okay, if we look at Charles's law, okay, I want you to notice that there's no pressure value. That's because this is related to a constant pressure situation. So basically an open container, or more precisely, excuse me, a flexible container. So one that is going to expand or contract and not alter the pressure of the situation that's being observed. Okay. We also have Gay-Lussac's law here, and that's actually occurring at constant volume. So what we mean here is that our container is rigid. So if you're carrying out a reaction in, let's say, like a bomb calorimeter or something that is a closed system, that would be a good example of a rigid container. So if we look at Charles's law with respect to volume and temperature graphically, you can see that volume and temperature are basically directly related. So at constant pressure, if you increase the temperature, you increase the volume, okay? Or if you increase the volume, you increase the temperature. So there's a direct relationship between volume and temperature. So once again, when you're doing calculations involving these specific situations, you want to make sure that temperature is in Kelvin. So anytime there's a temperature variable, make sure that you are in. Now another way to, I guess, visualize Charles's law is basically the expansion and contraction in a capillary tube of a gas that has a little bit of mercury covering it. So basically at low temperature, the gas particles are not moving around or expanding quite as much. If you increase the temperature, that volume is going to increase. Those particles of gas are going to separate out, and you subsequently get this change. Now, obviously, there has to be movement allowed within the container. So in this situation, obviously, a flexible container is what we see here. Okay, so let's look at this problem. It says a sample of carbon monoxide gas occupies 3.20 liters at 125 degrees C. At what temperature will the gas occupy a volume of 1.54 liters if the pressure remains constant? Okay, so we were given a volume value of 3.20 liters. We were given a temperature value of 125 degrees C. Okay, we were also given another volume value of 1.54 liters, okay, and they want us to calculate the temperature value at the new volume conditions. Now, obviously, the pressure, we've been told that the pressure remains constant, so we are not using the ideal gas law, but instead we're using Charles's law to do this calculation. So in this case, since pressure is not a component, we know that we're going to be using the V1 over T1 equals V2 over T2 equation. Okay, so we want to solve for the variable that we actually want to figure out. So we're going to cross up those T values. So V1 T2 equals V2 T1. Okay, get T2 all by itself. T2 is going to equal V2 T1 divided by V1. And we can take our variables and look and make sure that they are up to snuff in terms of the correct units. So if we check our volumes, we're in liters and liters, so those work out. Our temperature, though, is still in degrees C. And like we've said earlier, if there's temperature involved in the calculation, you must convert it to Kelvin. So we're going to add that 273.15. Okay, and this is going to give us 398.15 Kelvin. Okay, so we can now plug our numbers in. So T2 is going to be equal to 1.54 liters times T1, which is 398.15 Kelvin. Okay, divide that all out by our new, our old volume, our 3.20 liters. Okay, plug that into your calculator, and you're going to end up with 192 Kelvin, because liters and liters cancel, Kelvin is left over. Okay, this is the new temperature. So if we look at this, okay, we had a volume of 3.20 liters, and we decreased that volume to 1.54 liters. Okay, and we know that volume and temperature are directly related. So if the volume decreases, the temperature should also decrease. And so if we look at this from that perspective, we've gone from 398.15 Kelvin to 192 Kelvin. So both our volume and our temperature have decreased. So that makes sense with respect to the container, or with respect to the conditions in which the gas has been changed to. So this calculation is good. Okay, so here's another calculation that we're going to take a look at. Now, we've been told that we have a pressure in a car tire that is equal to 1.88 atm. Okay, we've been given a temperature value of 25 degrees C. Okay, and they want to know what will be the new pressure if the temperature warms up to 37 degrees C. Okay, so P2, they want to know what P2 is going to become if temperature 2 becomes 37 degrees C. Okay, so as we know, we need to convert this to Kelvin. Okay, plus 273 Kelvin. All right, so we convert both of our temperature values to the appropriate temperature. So after we've done that calculation set, we now have to check on which equation we're going to use. Okay, so there is no mention here of volume. Okay, so we're going to assume that that's a constant situation. Okay, so P1 over T1 equals P2 over T2. So in this situation, we're going to be solving for P2, so we're going to cross up those variables. P1 T2 is equal to P2 T1. Okay, get P2 all by itself. P2 is equal to P1 T2 divided by T1. Okay, so now we've set all this up. We can check our variables again, Kelvin and Kelvin, ATM, pressure is what we're solving for. Okay, so P2 is going to be equal to 1.88 ATM times 310.15 Kelvin divided by our T1, which is 298.15 Kelvin. Okay, so we plug all these in into our calculator, and that gives us 1.96. Okay, Kelvin and Kelvin cancel. ATM is what's left over. Okay, so 1.96 ATM. So let's look at the relationship here between our pressure and our temperature. So our temperature 1 is lower than our temperature 2. So we have increased the temperature. If we increase the temperature, we increase the speed of the molecules. They're moving around more. Okay, they're hitting the surface of the containers, right? So in this case, a rigid tire, right? Okay, it's not going to keep expanding. Okay, so those gas particles are going to bump into the sides of the container more and subsequently increase the pressure. And that's what we see. We see a slight increase in pressure overall. So this is Gay-Lussac's law, and as you can see, as long as you check your variables, you can subsequently plug in the appropriate values.